So in the first series of lectures, we looked at data that was perfect, right? I took an exponential equation and I used it to get some numbers. And that was fine because we really were trying to get an idea of how we could work with data and see things from data and infer things from data and come up with dynamical systems and difference equations and the whole 9 yards. And it was good to be able to do that without the interference of the data not being exact, because experimental data is really practically never exact. Right, so that's what we're going to do in this next series of lectures, is talk about how to handle that kind of real-world situation. So I've got some numbers here, and there's no context to them, right? And that's intentional. I want to talk about how we can come up with a model that describes this data without any kind of preconceived notions about what it is or how it should behave. All right, so when I have data like this, the first thing I'm going to do is I'm going to graph it. That's just going to kind of give me my first impression of what sort of shape the data is taking. And if I do that, you get something like this. And now this, at first glance, appears to pretty clearly be an exponential situation. However, the scale can be misleading. All right, these two values down here, for example, appear to be, well, they don't appear to be practically identical. They appear to be actually identical. And you can see from the data over here that they aren't. And the issue here is the scale, right? The difference between these two values is, well, it's exactly 4, right? Called 5 even. That's less than 10% of this interval. You're never going to be able to see that, right? So when you have a situation like this where the range is really large and some of your data is clustered in one part of it, one thing that it's a good idea to do is to zoom in, right? So that's what this next graph does. It just looks at those first 4 data values. And now we can see, yeah, it still has kind of that general exponential shape, although it's not as perfect. This value here that I highlighted a minute ago does look like, yeah, it's a little out of place. But not so much that I'm going to reject this idea out of hand. That one could just be a little bit of an outlier, or even just have a slightly higher error than the others. So I'm gonna proceed with this exponential model and see what we can get from that. So this is just a generic exponential equation, and what I need to do is find a value for a. And unfortunately, we don't have any really great tools for doing that. However, what we do have are a lot of tools for working with linear equations. We know what a linear equation looks like. We know how to find it given points. We know how to find its intercepts. We know how to find its rate of change. That's the slope, right? If I can transform this, if I can fiddle with this a little bit and turn it into a linear equation, then I've made some progress, right? So let's see. Here's what I'm going to do, right? I'm going to take the logarithm of both sides. I'm going to leave the left side the way it is, and I'm going to apply some logarithm rules over here on the right. I'm going to split this up, the log of a plus the log of e to the x. And the log of e to the x, well, that's just x, right? So this becomes the log of y equals the log of a plus x. And that is a linear equation, right? It's a linear equation if we treat this log of y as being a single variable, right? So here's what I'm going to do, right? Let's see how we can graph this and see what's going on. All right, so what I've done here is this is just our data again, and I've added a column. What I did is I just took the logarithm of all those y values. Okay, so now I'm going to graph this, And I'm going to, instead of using this y column, I'm going to kind of cross that out so we don't accidentally use it by mistake. Instead, I'm going to use the x values for the x-axis, and I'm going to use these log y numbers on the y-axis, and I'm going to call these y prime. Right now, you've probably taken a calculus class. You're probably used to thinking of that prime as meaning the derivative. We do use it to mean other things. All right. In this case, I'm using it to mean a new value that is derived. Yeah, I know, derivative, right? But that is derived from the previous y value. In this case, by taking the logarithm of it. All right. So if we graph these, I get this, and that looks familiar. Right? That sure looks like a linear equation. You see, once again, this 2 value is a little out of place, right? But that's okay. I'm still feeling pretty good about this. And now, again, notice what I've done, right? These are the x values down here. And notice how I've labeled the axis. These are the log of y values. So here for the first value for x equals 1, I didn't plot 8, I plotted 2.09, and I get this straight line. So this is awesome because we know how to work with these. So what do I need to do to come up with an equation here? Well, I know how to find the equation of the line. Now the methods that we have for doing that presume that it is a perfect line, and this clearly isn't. Right? Now there are a number of ways we can approach this. If you've taken a statistics class, or even maybe some algebra classes, you may have talked about linear regression and correlation coefficients and that kind of thing, and that's awesome. That's actually what we're going to talk about in the next couple of lectures here. For now, I'm just going to brute force this. I'm going to take the first point and the last point and find the slope through them. And so this will be 9.13 minus 2.09 divided by 8 minus 1, and that comes out to 1.005. All right, and then we can continue. We can find the y-intercept. I'm not going to make you sit and watch me do a basic algebra problem. You use the point slope equation here, and you end up with y equals 1.005x plus 1.087. Okay. Awesome. Well, I mean, that's great. Okay, we've got an equation, right? That's terrific. But it's not the equation that I wanted. I wanted to know what was that a parameter. All right, well, let's see how we can find that. Right? This log of a here, that is the y-intercept of my linear equation. And I know what that y-intercept was. It was 1.087. So in other words, the log of a equals 1.087. And that's an equation I can solve. Right, I'm going to convert this to the equivalent exponential equation. A equals e to the 1.087. And my calculator tells me that this is 2.9648. Well, let's call it 2.965. And that's what I needed to know. Right, so my model for this equation is y equals 2.965 e to the x. All right, now the next question we need to ask is this model any good? Right? Is this really giving us good results compared to the data values, which we are assuming to be the true values of the system that we're trying to describe? All right, and this is easy enough to test. So to test this, I've gone back to my original data. Right? What I'm going to do is I'm going to use my model to calculate the corresponding y prime values, if you will. Right? So, for example, I put 1 in for x, and I got this number, and I put 2 in for x, and I got this number, and so on. And you can see, just kind of eyeballing them here, they look Pretty decent. All right. So what I did next is kind of the next obvious thing. I calculated the percent error. So I took the difference of the two y's, the observed and the calculated, and I divided them by the observed value, which we're assuming is correct. And I got these percentages, which are not bad. I mean, those are some pretty decent results. You can tell something weird. I've been highlighting that second data value since the very first slide. Something weird happened there that we need to look into. Maybe it really is some strange anomaly that happens at the x=2 mark. More than likely, there was some kind of experimental error. Either way, that's something that bears looking into. But overall, these numbers are respectable, so I would be pretty comfortable sticking with this model here. Okay, so I want to talk about how I came up with this question for a minute. What I did is it's not real world, it's generated data. So what I did is I took an exponential model, an exponential formula, and I generated the exact results, and then I perturbed them a little bit, so they weren't perfect anymore. Right, and then I did all of these calculations, and obviously when you're doing something like you're teaching something like this, you want to show an example that works reasonably well, so students can see, what happens when it works. And I got all the way through to those percent error numbers, and they were all up in the 60 to 80% range. So, okay, this isn't going to work. I got to tweak the data, right? Just to make it a more representative example for us to look at. And all I did was I changed the y value for x=1, left all the others the same, and I got these results. Right, dramatic change just from changing one value. And the reason that happened is because of the way I calculated the slope, just kind of arbitrarily choosing the first and last values in the data set. That is really not a very good approach to finding the equation of a line from a data set. So that's the problem we're going to tackle in the next couple of lectures. Right? We're going to talk about how we can use all of the data values to find the best fit equation. Now, like I mentioned earlier, some of you have probably done this before with linear equations, linear correlation. We're going to take it a step further and see how you can use that same kind of approach to find the best fit polynomial. All right, so say you're looking at your data and you don't think it's linear, you think it's quadratic. Okay, well, there should be a way to find the best fit quadratic equation, just so you can find the best fit linear equation, right? And that's what we're going to be talking about next.